Hello, everyone. This is Rachel Hyosan, and I'm a PhD candidate in North Carolina State University. And today I'm going to present the work has been done with my advisor, Dr. Kevin Han. And this work is image acquisition planning for image-based 3D reconstruction using a robotic arm. So modular construction method brings a great benefit to the construction industry, fabricating building components in manufacturing plants and delivering them to the site for installation. So it improves the construction flows, better management of the schedule and costs, and safer working conditions, and the higher quality of the construction. So however, modular construction has challenges. One of the biggest challenge is the mismanagement of the prefabricated components. The modular method is fabricating and constructing in different locations. So delivering the damaged or wrong components to the site causes the rework, such as the design change, refabrication, and reshipping. So it can double the cost and schedule. Besides, construction in two different locations face the issue of the complicated permitting process. So permitting process for these modules vary state to state and country to country, since there are different building specification and jurisdiction for the construction. So module cannot be simply delivered on site without the local authorities, and finding a specialized inspector for approval in a manufacturing plant can be difficult if you think about the fabricated in overseas. So to overcome the issues, our idea is using visual construction management framework. So there is a recent research on the visual management platform called the CPMS, Construction Performance Modeling and Simulation. And the CPMS is capable of the comparison with the BIM and the reality model, as well as between the different reality models. So such a virtual environment allows the inspection between the construction and design model, also between the two reality models for adjoining parts for the modules. So this can manage the potential risk by checking it in a virtual environment before delivery. So right side of the figure shows that the snapshot of the visual inspection of the module in virtual environment. So to conduct the visual inspection in a virtual environment, visual data requires the quality. The quality factors are density and coverage, which means that the visual data requires to be dense and complete. Without the full coverage, it cannot finish the visual inspection of the other side, and the sparse visual data cannot identify correctly whether there are defects or not. So, and one of the factors we need to consider is that not much time is assigned for data collection. So we need an efficient and optimized operation for data acquisition. So to ensure the quality, our idea for data collection is using a camera attached robotic arm. And the idea consists of the two planning elements. One is the sensor planning, and the other one is the robotic arm motion planning. So sensor planning is finding sensor locations that can generate the 3D point cloud. And the robotic arm planning is to move the end effector through the sensor planned locations. And programmable robotic arm can automate the data collection task. Also, it assures the quality of the as-built model. So our testing method is summarized in this slide. Firstly, we choose the target object and we create the 3D model in CAD. And image taking positions are based on the field of view plane were decided on the 3D CAD model and made a trajectory plan for the robotic arm motion. After the robotic arm takes the images, we use the images to create an as-built model. So before we move into the planning motivation and the method, let me briefly overview how 3D model can be created by images. So it starts with the multiple image data, and features are extracted from the images, which are shown in the gray dots. Then find the relevant matching points between images. So using geometric relationship between the image and compute the 3D points of the corresponding points and find the relative camera pose and orientation. So the key of the technique is finding matches between the images and then compute the position of the match elements in the 3D space. So our motivation of the planning is to maintain the quality of the 3D reconstruction result. And the planning method uses the sensor planning and the robotic arm motion planning. So for the sensor planning method, we have found that correspondence error has a great influence on the 3D reconstruction results. So to reduce the error, it recommends keeping same distance from the image plane to object. So the figure A shows the how we set up the experiment, and the B shows the how the sensor planning elements are applied in experiment setup. So we focus on the 3 elements for the sensor planning. The first one is keeping our camera distance same to the object plane in each image taking location, and orientation of the image plane was parallel to the object surface. And to increase enough feature matching, the image overlap is also considered. And robotic arm has its own constraints in joint movement. So when the robotic arm reaches the constrained positions, the pose error increases, which means that the camera cannot be placed on the design location. So what we do here is identify the robotic arm workspace that can visit the image taking positions without the joint collision. So for this step, we survey the 3D discrete space, keeping camera distance and orientation. And when a robotic arm cannot correctly pose the space, then they are removed from the planning motion. So for instance, red crossed spots in the figure A. So image taking locations are selected, then trajectory has been decided to the move. So with the combination of the sensor and robotic arm planning, this video shows a quick demonstration of the robotic arm taking images for the object. So the design was taken pictures of when the robot arm was stopped so as to maintain the image quality. So the stopping location was chosen based on the overlap ratio, which is related to the interval between 2 consecutive images. So this factor is also related to number of the images. In case of 76% overlap has the 25 images, and 52% has this 9 images. So the result of the image overlap ratio was compared in the confidence level of the point cloud. And 4 cases constructed the point cloud model quite successfully, but the confidence level shows the differences. So increase the overlap ratio, increase the confidence level, which means that there are more points to determine the 3D point locations. This slide shows the summary of the result. So A shows the how camera attach and the factor move along the object surface to take the image data after sensor and the robotic arm planning. And B shows the image taken locations estimated with the 76% overlap after image processing. And C shows successfully reconstructed point cloud model. And the same trajectory was also performed in different objects, and the similar flat surface of the boxes and the concrete object like A and C was successfully reconstructed. And the concrete structure was bigger than the robotic arm workspace. So some of the parts are lack of data on the left side of the red outline. But similar size to the testing object was successfully reconstructed in C case. In cylinder pipe case is reconstructed partially except the bottom parts. So for the summary of the study, image-based 3D reconstruction method can be optimized and improved with the proposed method. So it provides a research direction, designing data collection method using robotic arms. And my future research plan is automating the sensor planning parts and applying it to the various shape of the building components so that we can improve and optimize the data collection step in construction. Thank you for your attention. And if you have any questions,